Hi, welcome to Math331, Lecture 8 sounds right, problem solving. So what I want to do today is I want to talk about Catalan functions. I want to do more with generating functions and show you how you can use these to set up a way to solve a variety of problems. Whether or not you can then actually do the algebra is another story. So we will see with the Catalan numbers, hopefully, that you actually can do the algebra. To try to make this a fair lecture, I have deliberately not slept last night. So I went to bed around 5:30. I have not looked at notes for this. So I am trying to put myself in as much as possible the mindset of somebody who does not know the Catalan numbers to try to influence what is going on. I will not do this for all lectures. But I thought for today I would try to do this so that I'm not trying to guide the algebra by knowing how it goes. It'll be interesting what happens in probability, but that's not your fault or your problem. All right, so let's start off with Catalan numbers. So like many things, Catalan numbers is a way of counting something we care about. It counts paths. Which paths? It counts paths on a square grid where you never cross the diagonal. So let's say it's 1, 2, 3, 4. One as fully drawn. I should never have drawn the diagonal line first. 1, 2, 3, 4. Plus 0. So I want to look at how many paths do I have where I do not cross the main diagonal. So I want to start down here. I want to end up here. And whatever path I take, I have to either go right or up at every turn, and I never cross the main line. And we'll call Cn the number of such paths, starting I think at 0, 0, and ending at n. So the first thing is, can you give me an upper bound or a lower bound? There's at least a trivial lower bound.
Oh, lower bound?
Yeah.
1.
1. Also would have accepted 0, 0 unless you go to 1, unless you go to C. You know, start small. Let's get something on the board. Upper bound. Yes.
10 to 5.
Okay, that's for this specific board. So I want an upper bound that will work in general, but good. So if it's an n by n board.
2n, choose n.
Good. So that's not a bad upper bound. Right? And in fact, we even know something about how large 2n choose n is. Well, you'd have 2n factorial over n factorial n factorial. Does anybody know a decent bound for 2n choose n? Just give you some rough idea of size. You always want to have a sense of size. So I claim this is less than 2 to the 2n. And the reason is the binomial theorem. X plus y to the m is the sum of m choose k, x to the k, y to the m minus k. K goes from 0 to m. So just from the binomial theorem, one term is going to be less than or equal to the sum of all the terms. Just take x equals y equals 1, take m equals 2n. And in fact, this is not a terrible estimate because this is the largest term. So we know that all the other terms are at most this. So you could actually get something a little bit better. All right. It turns out, not surprisingly, the answer is much closer to 2n choose n than it is to 1. All right. So my first question is, can you give me any non-trivial bounds? You know, here's 0, here's n, and I want to look at the number of paths. Any thoughts on how I would get a decent lower bound? So we're doing Catalan numbers that count the number of paths on an n by n grid where you don't cross the main diagonal. We just got an upper bound. We're trying to get a reasonable lower bound. Yes. Did you have a hand up?
Can I ask a question?
Sure.
How is it not exactly 2n choose n? Because you have like 2n, you have to move right at least n times.
Mm-hmm.
You have to move up at least n times, and you have to
So
interleave.
2n choose n would be all the paths from here to here. We have to stay on or below the main diagonal. We can only live in this path down here. We can't cross the main diagonal.
I see.
So if we just wanted to count the number of paths, it would be 2n choose n, absolutely. But we want to stay down below.
2n.
Okay, why would it be 2n?
You could just move to the right and up until you get to the end or no.
Okay, but that's only one specific path. That would give you, now, so you would have the path of going straight across and then straight up, or you could have over, up, over, up, over, up, over, up. And as long as n is at least 2, then you would have a lower bound of 2. But that's not going to be a lower bound that grows with n.
This might be silly, but you just divide it by 2 since it like cuts the board in half.
So the idea was, can we just divide this in 2 and say, look, we either got a path in the bottom or a path in the top. The problem is you could have a path that's below for a while, then above, then below again, and then above again. So the problem is you cannot uniquely assign. Then if you have a path that is just on the diagonal, that might actually even be counted by, well, unfortunately you can't be on the diagonal too often. You have to go off when you go right or off when you go up. Yes?
Can we try 2n choose n minus 2n minus 1 choose n minus 1?
All right, so is the first one 2n choose n and then is it minus, yes?
Yeah, 2n minus 1 over n minus 1.
Okay, how did you get that?
So those are just all the paths where you go up first.
Okay.
So those are immediately disqualified.
I see. So 2n choose n is the total number of paths.
Yes.
And then this is removing, yes.
Just like fixing the first move to be
Yes.
straight up.
So this will give you a slightly better upper bound. Yes. Excellent. So we will now have that, Cn will be less than or equal to that. The question is, can we get a good lower bound? And so here's a great way to get a lower bound. What makes this problem complicated is the fact that we can't cross the main diagonal, right? We would love to be in a situation where we could just move freely. I claim there's a really good point down here where we could go to first, and then we would have a long stretch of time when we could move freely. We're not going to get every path. Where should we move to?
If you go one short of the end.
Okay, we go one short to the end, then we're not going to, okay.
You can move freely.
Then you can move freely from that point onward. Well, you could actually overshoot up, but that would be the only thing you'd have to worry about. So if you move to one short of the end, then you have one right remaining, and you have n ups remaining. So that would essentially give you a bound of n, which is at least a bound that grows to infinity, right? So we at least have that the Catalan numbers go to infinity. This is a no shit statement, right? When you look at this board, the number of paths should be growing rapidly. We'll have to put like a language warning on this. But at least, okay, well then what if we just went too short? Well, then we could almost go all the way up to the top, right? So if we were too short, we would have 2 rights, and we would still have n ups. And the only thing that would fail is if we go up too far in the beginning. So what we would have that would be free is we would have 2 rights and n minus 2 ups. We could do all of that freely. And that will give us n choose 2 as a lower bound. Right? So what I like about this is, again, I do not care about the answer today. In my research, I actually care about them. I use the Catalan numbers all the time in my research. But today, I don't care about the specific answers. You should really not care about the specific answers. It is unlikely you will use the Catalan numbers once you leave Williams. But the idea of how to take even a trivial case, get something and then continue to exploit it. So again, for those of you who came in late, I have deliberately not slept that much tonight. I got about an hour's sleep to try to have myself in a state where I really do not know what I'm going to say. To just try to look at this problem from a fresh perspective. So we said, well, look, if we just go over and just leave just one point here, yes.
Well, you get the biggest value from going halfway. Right?
Yes, if you go halfway. So if we then went 3 over, we would then have, in that case, we would have 3 rights and ups. And so what would be free would be 3 rights and n minus 3 ups. And that would lead to a lower bound of n choose 3 for less than or equal to Cn. And so we can keep doing this. We can say, well, what's going to give us the greatest freedom? The greatest freedom is, oh, well, we want that to be half because the middle binomial coefficient is the largest. So the best for us would be to do n halves rights. And we never worry if something is not an integer. So we'd have n halves rights and n halves ups. And we have n choose n minus 2. And if you want to look at this, what's really going on is we're saying the following. We walk down like this, always to the right. And then we go any way we want to this upper right corner. And then from this upper right corner, then we walk straight up. Oh, well, that's not so bad now as a lower bound. Because this is the largest binomial coefficient, this is greater than or equal to 2 to the n divided by n plus 1. Because if you look at x plus y to the n, there are n plus 1 terms. The sum of all the binomial coefficients is 2 to the n. This is the largest. So if I replace all of the binomial coefficients with n choose n halves, I've made them larger. So since this is the largest, it's got to be at least as large as the average value, which is 2n over n plus 1. Well, this isn't so bad now. Now again, 2 to the 2n grows a lot faster than 2 to the n. But we at least have its approximate scale now. It's growing somewhere between 2 to the n and 4 to the n, essentially. So we know it's growing exponentially fast. And we have some rough idea even what that exponent is. It's not perfect, but we have an idea. So, to me, there's tremendous power in doing analysis like this. And getting a sense of having a free parameter. So we had a free parameter. Notice how much we improved things. The initial suggestion came from the audience, right? With a little bit of a hint of me saying, let's try to look at it. But it said, move over just one spot from the end. And that gave us essentially a lower bound of n. A lower bound of n is very far from 2 to the 2n. That's linear, that's polynomial versus exponential. But then we said, well, then we could move over just all but 2, all but 3. And then where's the best place to go? Something to optimize. And now we're fairly close. All right, so this is probably a good place to stop in terms of just trying to get a sense of the size of the answer. The answer is going to be much closer to 2 to the 2n than it is going to be to 2 to the n. And if you want, you can think, this is pretty damn wasteful over here, right? We're forcing us to go straight to the right that many times? So then the question is, well, could we start maybe doing things a little bit better? What if we went over maybe n4th, and then we played things like that? And could you somehow make an argument like this to get a better lower bound? If you want, as an extra credit, try to see how far you could push something like this in breaking it up into a couple of places. I don't have a desire to do that right now, but it's definitely something you could push. All right. So what we want to do now is we want to come up with a recurrence relation. So we talked about recurrence relations for the Fibonacci numbers. So the Fibonacci's was fn plus 1 is fn plus fn minus 1, and typically f0 is 0, f1 is 1. And once you know those two initial conditions, everything's uniquely determined. We can sort of get a generating function. G of x is the sum and goes from 0 to infinity of fn x to the n. And after some algebra, we got that this equaled, I think, x over 1 minus x squared. And the idea is, this may seem strange to do because we don't know what the Fibonacci numbers are. How can we build a function when we do know what they are? Once I give you the recurrence relation, everything about them is known. The reason this is useful is that there's a nice closed form expression for g of x, and then we get to use our least favorite technique from calculus. So have you taken calculus?
Yes.
Have you taken integration?
Yes.
What is your least favorite technique to integrate?
By hand.
Of the methods by hand, which one do you prefer not to use?
By parts.
No, you're not allowed to say that. I will actually no longer serve as your colloquium advisor.
Oh no.
Okay, that's not a protected category. You have to like integration by parts. You have to like U substitution.
Okay.
Those are friendly. What's your least favorite technique? Do you remember? Or have you blocked out the memory because it's so bad?
I don't know. I've only done it using the fundamental theorem.
Okay, partial fractions. Usually once people remember that they've seen partial fractions, they remember that they hated it. And so you have to use partial fractions for something like this, but then it leads to Benet's formula. Namely, that the nth Fibonacci number is the sum and goes from, is 1 over square root of 5, the golden mean 1 plus root 5 over 2 to the n, minus 1 over square root of 5, 1 minus root 5 over 2 to the n. Just by using partial fractions to expand this out and the geometric series. So I'll say partial fractions, and I'll say geometric series. And now we have an explicit formula for the nth Fibonacci number. We can just jump to any Fibonacci number. This is a terrific relation, and since this term is exponentially small, this term doesn't really matter in the limit. It's just dominated by this one. So the question is there a similar formula for Catalan numbers? Can we write down an explicit formula for the nth Catalan numbers? And it turns out these numbers arise in a huge number of applications. What do you think the answer is? Yes, I'm giving this lecture. Right? I'm so confident I deliberately did not sleep so I would not have any of the algebra in my mind. I have not looked at my notes. It's supposed to be so follow your nose, I have no choice but to get to the right answer. Okay? The difficulty is here we have the recurrence relation. We do not initially have a recurrence relation for the Catalan numbers. We need to find that recurrence relation. Once we find the recurrence relation, we will then form the generating function. Then once we have the generating function, we will do algebra and hopefully get a nice explicit closed form expression for the generating function. And then hopefully from that, we'll be able to extract an explicit formula for the nth one. All right? Are we clear on the game plan? I'd like to erase this to just keep the entire board available. To be honest, I have absolutely no idea how much space I'm going to need for this. Everybody good? All right. So the first thing is we have to find the new recurrence relation. And so the challenge is always the right perspective, what to look for. And so I've done this so many times. I need to look at all the paths, and I want to write a recurrence relation. So I want to express it in terms of previous things. We know we start here. We know we end here. Is it possible we get from here to here without ever hitting the diagonal? No, why not?
The end is on it.
The end is on it. So we know we have to hit the diagonal at least here. Is it possible that that's the only place we hit it? Absolutely. There's many paths that only hit it for the first time and the last time there. I feel like Spaceballs now. Is it possible that we first hit it some other place? Yeah. Is it possible we hit the diagonal many times? What we can do is we can break things up based on where do you first hit. We will not count this as a first hit, because otherwise then this is stupid. Right? So call it, if you want, the first return. All right, let's look for the first return. So the first return, so let's say the first return is at the point k comma k. So we have some path, and it gets us to there. Yes?
So, that's c to the k.
Yes, what, I'm sorry?
That's the Catalan number for k.
What's the Catalan number for k? We have to use very explicit
The
words.
number of ways to hit at k to the k.
The number of ways to hit k to the k
Without
is c to the k.
crossing the diagonal at all.
Without crossing the diagonal at all. But could you be on the diagonal?
Yes.
And so this has to be the first hit is at k. And what you just said is maybe the number of paths to get here, I agree, is ck. But you could have hit it earlier. Right? And so you will be counting things you should not be allowed to count. Yes?
Would it be ck minus the summation as like I goes from 1 to k minus 1 of c sub I? Because then you're
Okay, so what you want to do is you want to subtract off smaller things. But you've got to be careful that you don't subtract off something too many times. Right? Maybe this path gets credited multiple times.
Oh, yeah.
So let me do a zoom in. Here's 0, 0. Here's KK. One of my daughter's nicknames. What do we know about our first move?
Right.
Has to be right. What do we know about our last move? Has to be up. Ah. Now what do I do?
You make it like a smaller.
I make it a smaller one over here. Right? And now I do the Catalan numbers for this triangle. And then as long as I do a Catalan path here, I'll never cross this. I can be on it, and this I'll never reach this. How many ways can I do that? C sub k minus 1. And now, how many ways can I get from here to the end? And I don't care if I cross the diagonal multiple times, because my paths will be distinguished because each path will have a first hit. How many ways are there from here to here? C sub n minus k. So the first return at k gives c k minus 1, c n minus k. And so we now have a beautiful recurrence relation. Might be slightly out of focus. Alright. So now we would get Cn equals the sum, k goes from something to something, of c k minus 1, Cn minus k. What's the smallest value k could be? 1. And what's the largest value k could be? N. And we'll have the initial condition C0 is equal to 1. The number of ways to go from 0, 0 to 1, 1 is just this one path. I've got to go right then up. So C0 equals 1, C1 equals 1. We'll say C0 is the number of ways to go from 0, 0 to 0, 0. There's one way to do it. I think that's what we want. Okay, so now we have a formula. So I'll write it over here large. So Cn is the sum, k goes from 1 to n, of ck minus 1, Cn minus k. Well, let's change the variables. Let's let L equal k minus 1. So now we get Cn is going to be the sum, L goes from 0 to n minus 1, of Cl, and now Cn minus k, so it's Cn minus k minus 1, so it's a plus 1, so I have to subtract 1, so it's going to be n minus 1 minus L. Right? So it actually might even be easier to study Cn plus 1 is the sum, L goes from 0 to n, of Cl, Cn minus L. That just looks a little bit nicer. That the n plus first coefficient is this nice product. And we'll put in C0 equals C1 equals 1. There's our recurrence relation. This is night and day from the Fibonacci recurrence. It is not a fixed length. The length actually grows as it gets bigger. Okay, that's one issue. The other issue is it's not linear. It's actually quadratic. Is what it is. But there's a nice interpretation of this. And this goes back a little bit to some of the inequalities we were studying before. That sometimes the way a problem is written hides what's going on. So instead of studying CL, Cn minus L, what would be a more general thing to study in terms of sequences? So I'm going to introduce something called the convolution. So if we have two sequences, A is the sequence, AN, and B is the sequence BN, then A star B is the sum, the nth term of that will be the sum, L goes from 0 to n, of A, L, B, n minus L. And by symmetry, what is A star B the same as? B star A. So what do we say if the order doesn't matter? The relation is commutative. So order doesn't matter, which is nice. Let's think about what's going on. Imagine you have the polynomial A0 plus A1x plus A2x squared plus dot dot dot. And you multiply by the polynomial B0 plus B1x plus B2x squared. Okay, how many of you know what an engineering hat is, or a physics hat, or an economics hat is? No? You put this hat on, and then you no longer have to worry about convergence arguments. It basically says, I trust the mathematicians. When you multiply infinite series, you absolutely have to worry about convergence. And in fact, this is one of the reasons why I wanted some rough estimates as to how rapidly do these numbers grow. They grow at most at the rate 2 to the 2n. So if I take x to be sufficiently small, the series will converge, and I can justify everything that I'm doing. But if I have two series, if they converge and their products converge, I can multiply them. What's the constant term going to be when I multiply them out? A0, B0. What's the linear term, the x term? Yes, but I'm going to write it in the other order so that it matches what I have up here. I'll write it as A0 times B1 plus A1 times B0 x. And then I'll do the quadratic term, which will be A0 B2 plus A1 B1 plus A2 B0 x squared, and so on and so on and so on. That if I take the convolution of two series, then the coefficient has this wonderful form. What we're doing is now just the special case when A equals B equals C. Because we're convolving the Catalan numbers with themselves. Okay? So is everybody clear on what this convolution is doing? It's a wonderful operation. In my probability class, we will do a lot with convolutions later on. It allows you to take two series and combine them. And again, I might want these things to be converging. If I know the A's are growing at a certain rate, then as long as x is sufficiently small, it's going to be dominated by a geometric series and it will converge. For the Catalan numbers, we know the nth Catalan number is at most 2 to the 2n, also known as 4 to the n. So if I take x to be at most, to be less than 1/4, say x is 1/5, then everything is going to converge. It'll be bounded by a geometric series that converges. So it's a nice exercise. It's worth arguing that things will converge. And now we can use this to actually analyze the Catalan numbers. So one of the things we have to be a little bit careful of is, annoyingly, our series is starting off with the Cn plus 1 is that. All right, it's just a small shift. It's not a huge deal. But what we're seeing again and again and again is the power of looking at things the right way. Is if we break things up based on when is the first time you return to the main diagonal, then we got a really nice recurrence relation. And we didn't have to worry, well, I returned here, but I also returned here, and doing this terrible inclusion-exclusion nightmare. So now, let's define g of x to be the sum, n goes from 0 to infinity, of Cn x to the n. We're okay if the absolute value of x is strictly less than 1/4. As we know, Cn is less than or equal to 4 to the n. So everything will be fine in that window. And we know that Cn plus 1 is just what comes on when we do the convolution of g with g. So if we look at g of x squared, this is going to be the sum, and goes from 0 to infinity. Well, let's use maybe L goes from 0 to infinity of CL x to the L times the sum of maybe m goes from 0 to infinity of Cm x to the m. I can't use the same letter twice, or at least I shouldn't. And we know that this is going to be related to our sequence. So let's see what happens. So I'm going to say that this is the sum n goes from 0 to infinity. We will have the sum L goes from 0 to n, CL, c to the n minus L. Right? X to the n. Because if I want to get a term of x to the n, if I take x to the L here, I have to take x to the n minus L here. And I can do this for n equals 0, for n equals 1, for n equals 2. And what do we know about this number here? What does that equal? By our recurrence relation, yes?
So n plus 1.
So this is the sum, n goes from 0 to infinity, of Cn plus 1 x to the n. So when you look at this, if you could change one part of this, what would you change? Yeah, just make it x to the n plus 1. This violates the 13th, 14th, and 15th Amendments to the U.S. Constitution. You cannot do one thing to just one side of the equation. That is discrimination. We will not do that in this classroom. So if you want to make that an n plus 1, what do you need to do? Pull out 1 over x. Now everything is fine. So you get g of x squared is 1 over x. So really the only term we're missing is the n equals 0 term. That's not bad. So we can erase the general theory of convolutions, because now we are applying the theory of convolutions. Okay. Let's take this one. So now we get g of x squared times x is equal to g of x minus the 0th term. The 0th term is just 1. Okay? Does everybody agree with this? Because our sum, since we now have Cn plus 1 x to the n plus 1, we're just missing the C0 x to the 0 term. So we have to add that, and then we have to subtract that. So now we get x g of x squared minus g of x plus 1 equals 0. What should we do? Thoughts? How can we solve for g of x? Quadratic equation, right? We have a quadratic. What is our unknown? Our unknown is g of x. So we get g of x is negative b plus or minus square root of b squared minus 4ac all over 2a. Everybody knows the song, right? Negative b is going to be 1 plus or minus the square root of b squared minus 4ac, I think 4x, divided by 2a. Okay? There are now two solutions for the generating function. Do you like both solutions?
Is the minus one a decreasing function?
No.
Because you got to be careful because you've got x upstairs and downstairs. So remember, and in fact, we said x was less than a fourth. You can see quite clearly over here, we want x to be less than a fourth. If x was 1/4, it's just barely okay. If x is greater than a fourth, you would now have a negative number, and you'd be taking the square root of that, and you'd be having a huge problem. Do we agree that at least one of the two solutions should be bad? But it's not immediately clear which, because unfortunately, this quantity here will be less than 1, so even if we subtracted it, it would be less than 1. All right. So before we used partial fractions, right? We could actually use the generalized binomial theorem for the square root of 1 minus 4x. Remember, we actually know how the series begins. We know what C0 is. We know what C1 is. We know what C2 is. Or if we don't know what C2 is, we can compute it by brute force. We could see which one of these agrees with the small values. So now what we need to do is we need Newton's generalized binomial theorem. How many of you have seen the generalized binomial theorem? Okay. This is one of the nice things about this class. You should have seen this. This is probably the only time when we can actually correct omissions in your education. Okay. Let's spend some time and let's look at Newton's generalized binomial. This will actually give me an opportunity to talk about how almost surely you were not taught math properly. Or at least something was hidden. So we are damn close at this point. Let me just talk to you a little bit about differentiation. What's the derivative of x cubed? 3x squared. What's the derivative of x to the 4/3? And x to the square root of 2, its derivative is? All right. You got them all right. Their proofs are very different. The proof of the first one, how do we prove what the derivative of the first one is? Well, we use x plus h cubed minus x cubed over h, and we take the limit as h goes to 0. And we just expand out the x plus h cubed. We use the binomial theorem, or we use something, and we see that it's going to look like it's going to look like x cubed plus 3hx squared, and then everything else will have at least an h squared. That's how we take the derivative here. Does anybody know how we take the derivative of x to the 4/3? We can't just do x plus h to the 4/3. We would have to know how do you expand out x plus h to the 4/3. What you do is, if f of x is x to the 4/3, let g of x be f of x cubed is x to the 4th. And now we can take the derivative of both of these, and we use the power rule. It's 3 f of x squared, f prime of x is 4x cubed. And so you get g prime of x is 3 f of x squared, f prime of x is 4x cubed. Solving for f prime of x, you get 4x cubed over 3 f of x squared, and then you just substitute in for f of x. That's how you take the derivative of this one. The last one is what does x to the root 2 even mean? This is the same as e to the log of x to the root 2 is e to the root 2 log x. And now you have to use the chain rule. And you represent this as an infinite series. So this point is almost always glossed over in calculus classes. To some extent, it should be glossed over a little bit when you're doing, Calc 1. But you should be at least aware that there's something that's being glossed over. That there is a subtlety in taking the derivative of x to the 4/3, or of taking x to the root 2. What does it even mean to say x to the root 2? You can plug it into your calculator will give it to you without any trouble. But more work is needed. So let's go back now to what we have. So we have the generating function is equal to, it was 1 plus or minus the square root of 1 minus 4x all over 2x. Right? Let's look at f of x is 1 plus ax to the 1/2. This will be a very special case of Newton's binomial theorem. Okay? And now, let's calculate derivatives. And I guess we'll start off with here. What does f of 0 equal? So f of 0 is 1. So now, f prime of x is going to be 1/2, 1 plus ax, and then we're going to get an a coming out. Right? F prime of 0 to the negative 1/2, yes. Sorry. What will f prime of 0 be? Just a halves. I'm sorry? Right. F double prime of x will be 1/2, and now we'll have a negative 1/2. 1 plus ax to the negative 3/2 a squared. F double prime of 0 is going to be negative a squared over 2 times 2. It's not clear yet what the pattern is. F triple prime of x is going to be 1/2, negative 1/2, and now what comes next? Negative 3/2, 1 plus a to the negative 5/2 a cubed. F triple prime of 0 is negative a cubed over 2 times 2 times 2. It's going to be a positive sign now, right? And it's going to be a 1 times 3. So in fact, it might be easier if I actually just might make this a negative sign to begin with. Because if I make that a negative sign to begin with, then when I take the derivative here, I'll have a negative. And then on the next one, it'll still be a negative. So it'll always be negative. So if I just make this a negative sign, I think it's going to make the algebra a little bit nicer. So we'll always have a negative. Let's do one more. The fourth derivative would be negative 1 over 2, negative 1 over 2, negative 3 over 2, negative 5 over 2, 1 minus a to the negative 7/2, a to the 4th. So the fourth derivative at 0 would be a to the 4th with a negative sign, 1 times 3 times 5 times 7 over, all right, fine. I know 7. All right. Is the pattern looking clear? So this is a double factorial. Double factorial means every other. All right, we've got 5 minutes left. Do you think we can do it? So we'll say the nth derivative at 0 is going to be negative a. So the third derivative we had an a cubed, so it'll be an a to the n. We have, here we have 3 2's, here we have 4 2's. All right.
Why
So
is the a to the fourth root negative?
they're all negative now.
Oh,
So we'll have 2 to the n down below, right? And now, for the fourth term, we stop at 5. For the third term, we stop at 3. So it's the problem is things are slightly shifted, but all right. So we'll go. The number of terms we have is 1 less than n. So here we have 4. We only have 3 terms. All right. So we have 1 times 3 times 5, all the way up to, I think it's 2n minus 8. So I'm going to do n plus 1. And we'll have an n plus 1 over here. We'll have an n plus 1 over here. And I think we go all the way up to 2n minus 1. Okay? So I think that's right. And so, for instance, for the n plus 1 here would be 7. So I think this is good. All right. What does the top look like with the double factorials? What would you much rather have rather than the double factorials? You'd rather just have the factorials. So let's multiply this by what we're missing. So we're missing all the evens. So we have a 2n double factorial. So let's put a 2n double factorial over here. Okay? And now if we do this, we get negative a to the n plus 1, 2n factorial, divided by 2 times 2 to the n times 2n double factorial. But when you look at your coefficient in your series, my g of x is going to be the sum, n goes from 0 to infinity, of the nth derivative at 0 divided by n factorial times x to the n. So if I want to get my coefficient cn plus 1, I get to divide by like an n plus 1 factorial. So my cn plus 1 will be my n plus first, I think, coefficient at 0 divided by n plus 1 factorial. Right? Because when we do Taylor series, it's the nth derivative divided by n factorial. Again, my algebra could easily be shifted off by 1. Not really that concerned. I will get then a negative a to the n plus 1. I have a 2n factorial. Downstairs, I have a 2 times 2 to the n, 2n double factorial, and then I have an n plus 1 factorial. Well, the 2n double factorial, that's all the evens. That's the same as n factorial times 2 to the n. This is just 2 to the n times n factorial, because each term has an even number. So we get cn plus 1 is going to be like negative a n plus 1 2n factorial over 2 times 2 to the n times 2 to the n times n factorial times n factorial times n plus 1 factorial. So I'll get something like negative a to the n plus 1 over 2 times 4 to the n 2n choose n. And then there's also a 1 over n plus 1. At this point, we're just doing algebra. So for us, what does a equal? A equals 4. So the 4 to the n is basically going to cancel this. for us, A equals 4. And so we will get basically negative 1 over, I guess negative 2, sorry, negative 2, 1 over n plus 1, 2n choose n. And so the only mistake I made is this isn't Cn. This is just expanding out the 1 minus 4x. So let me call this with a hat. And so we can see essentially what this is. Now we have the expansion for this. The 2x is going to shift. Oh, that 2 is going to cancel that factor of 2. We now see we want the minus sign here, because the minus sign and the minus sign will make it positive. It has to be a positive coefficient. So when the dust settles, we will actually get Cn is 1 over n plus 1, 2n choose n. So we slightly ran out of time at the end. I'll send you some notes. But the idea is we figured out what the right expansion of this was. And the only one that's going to work is the one with the minus sign. And now we have an explicit formula for the nth Catalan number. It's 2n choose n divided by n plus 1. So it's extremely close to the